morning. You are welcome to this section. I am Maria Pia Fanti. I will be the chair of this section. The title of the section is Task and Resource Allocation. We will have four presentations. Each presentation will be of 15 minutes with 5 minutes for questions. Please write the request for the question in the chat, and we will give you the possibility to talk to make the question. Now I will present the first speaker, that is Mirko Mazzoleni. He will present a multi-period asset allocation via kernel-based control. Please, Mirko. I don't hear you. Okay.
Good morning. I'm Mirko Mazzoleni from University of Bergamo, and I will present a work entitled Multi-Period Asset Allocation via Kernel-Based Control. This is a work being made by Gabriele Maroni and Fabio Previdi from University of Bergamo and Simone Formentin from Politecnico di Milano. I'm presenting here as at behalf of the author, and I will try to do my best to present this work. So this is the outline of my presentation. We will start with reviewing the intersections between control engineering and finance. Then we will describe the problem statement, and we look at the multi-period portfolio optimization with linear investment laws, which is an approach that is present in the literature. Then we'll extend this approach with non-linear investment laws, and we'll show experimental results, and then we'll draw some conclusions. So let's start with the first topic. Control engineering deals with controlling a process to make it behave as desired. And in finance, we want to deal with how individuals and organizations control the resource state. In control, we can do this by means of an appropriate control action. And in finance, we do this through investment choices. In control, we want to do this although the presence of unpredictable external disturbances which act on the process. While in finance, we want to make our investment choices even if they are subject to uncertain economics and political events. And so these are some similarities between control engineering and finance. Let's say we can approach a investment problem from a control engineering perspective. So which is the main investment strategies that we can use? We have three types of investment strategies. The first one is the so-called fundamental analysis that tries to quantify the intrinsic value of companies' securities based on economic factors such as earnings and dividends. Then there is technical analysis, which seeks to trading opportunities based on statistical analysis of past price pattern and trade volumes. And then we have quantitative analysis, which use mathematical models and large data set to analyze financial markets and securities. In this presentation, we will focus on a quantitative analysis approach. So we want to tackle portfolio optimization. Portfolio optimization aims to determine the best allocation of resources to different financial assets. And we can have single period portfolio optimization. That is, the allocation problem is treated as a single decision step over the considered time period. And then we can have multi-period portfolio optimization, where the allocation problem is treated as a series of multiple decision steps over the considered period. In the first case, if no transaction costs are present, then we can solve again the single period problem for successive time periods, making it a multi-period optimization problem. But if transaction costs are present, present, this is a not efficient approach. And then we need to resort to natural multi-period portfolio optimization techniques. And for this purpose, methods based on predictive control can naturally handle constraints on the portfolio composition and are also suitable for practical implementations. So these are the main quantities that were proposed in the literature. We consider a collection of n risky assets, A1 to AN, and the investment timeline is divided into T periods of a certain duration. Then the state X is the portfolio vector at time K, and basically it consists of a monetary amount allocated to the asset AI at time K. If Xi is less than 0, this means that we are in a short position, so we sold the quantities before having them. Otherwise, we are in a long position, so we bought some quantities. And with the letter W, we indicate the total wealth at the time K, and this is basically the sum of our state vector X. And with U, our control action, and this is the vector of transaction at the time K. If U is greater than 0, we buy the asset E. If UI is less than 0, we sell the asset I. And then we have the quantity R, which is the return vector at time K, and the return I is defined basically a relative variation of the price of the asset I. And the gain vector is defined as the ratio between the current price of the asset I and the price of the same asset at the previous time step. Then the portfolio dynamics can be described in this way, by considering that the investor may gain or lose money depending on the price return. So our dynamics can be expressed as the matrix G, which is a gain matrix, is the diagonal matrix that has the gains on its diagonal, and controlled by a control action U, with which consists in our transaction, our investment decisions. And okay, we can cast this problem as a multi-period portfolio optimization. In particular, here we suppose to have at disposal big N AID scenarios of the gain vector, so realization of the gain vector G. And in this way, we can construct the cost function that we call expected shortfall, as defined as the average of the difference. So we want to minimize this cost function that is a sort of error because it contains an error between gamma, which is a given wealth target, and the actual target obtained in the scenario J. And obviously we do not want to penalize the fact that if we gain more than expected, so we do not penalize this, and so this is the reason for having this max. And we can define a closed loop investment policy, which is composed by two components. The first one we call the U bar. It is a base policy, and then a correction term which weights with some weight theta the difference between the actual gain and the estimated gains G bar. So by using a linear policy as this, linear in the parameters theta, it is possible to show that this choice led to a convex problem. And this is actually what has been proposed in the literature. And we want to minimize our expected shortfall cost function in order to estimate the optimal policy, which is composed by U bar and theta for each time stamp from 0 to t minus 1. Subject to some constraint, that is our portfolio has to satisfy the portfolio dynamics that we derived some slides before, and also that the portfolio should be self-financing. So we do not put more money in our portfolio, but the wealth redistribute in the different assets. And we want to do this for each timestamp K and for every, considering all the J scenarios. And to avoid the non-differentiability of the max, we can consider slack variables. And the quantity u bar 0 has to be defined beforehand. And our contribution was to move from linear to non-linear investment laws. So it is reasonable to ask whether a linear parameterization is sufficient to capture the market dynamics. And we can extend the linear policy to non-linear ones. So given the sequence of market realization from G1 to GK, we look for general policies that are function of the observed gains. So we have this function here, Fk, that actually maps from all the gains to a different function for each asset I. And we will consider two approaches, one based on nonlinear input transforms and one based on kernel methods. So the first approach, we consider here a linear control policy for the asset AI with memory tau, where we define this vector of gains G tau that contains all the gains for each asset from K to tau steps before, where beta I is a vector of weights for the asset AI. And a first way to move into nonlinear control laws is to introduce a feature map, such that this vector of gains G tau is mapped to another dimension, which I call D. And then just substitute the linear control policy of the approach from the literature with, again, a policy which is indeed linear in the parameter beta, but non-linear in the original feature vector G. So the optimization problem is very similar to the one that we saw before, apart from the fact that now we introduced an additional regularization term to avoid overfitting the data. And this is one way to move to nonlinear control laws. We can do one step further by using kernel methods. Actually, kernel methods allow to implicitly define this feature map phi by using the so-called kernel function. So using the representer theorem that is the main theorem from kernel learning approaches, we know that there exists a vector that I call Ci for the asset AI, such that the function that controls the asset I at time k can be represented as a linear combination of the kernel function weighted by the component of this vector Ci, where Cit denotes the T element of the vector Ci. And so kernel methods are usually endowed with a Tikhonov regularization term that penalize two varying functions. So we strive for smoother functions, where H is a so-called reproducing kernel inverse space. So it is a space of functions that is induced by the kernel. So using the representer theorem, we can write the regularization term in this way, where K is the so-called kernel matrix, and it is composed by evaluating the kernel in all our feature elements. So we can build up a new optimization problem that now consists in, again, finding the base policy U bar and all the coefficients C for our kernel learning problem. And again, we have the same constraints on portfolio dynamics and the self-financing property. And now the control law is defined by the function that we learned with the kernel here. So we try to evaluate these approaches by considering a multi-period allocation problem involving 7 assets and a planning horizon of 12 periods, each having the duration of 1 trading month. And historical data of monthly asset returns were gathered from Yahoo Finance from 2007 to 2019. And these are the same assets used in this contribution present in the literature. And actually, these are the time behavior of the assets. and we divided them in two groups, one for the training and one for the testing of the approaches. Actually, the training set, it is used to generate two sets of scenarios by using Bootstrap. And each of these two sets is composed by 200 realizations of our 12 periods for a total of 2014 samples per set. And the first scenario was used as a training set to compute the optimal allocation strategies. And the second one was used as a validation set for tuning the hyperparameters of the method, such as the regularization strength. And then the test set is used to generate a third scenario to test the strategies. And we compare the following strategies. The first one is the affine policy with a single memory. The second one is, again, affine policies with a two-order memory. Then we compare a policy with squared transformation of the inputs, a policy that uses kernel methods, actually with a Gaussian kernel, and then the uniform or naive policy, that is a fraction 1 over n of investor wealth is allocated to each of the n assets at each rebalancing stage. And these are the result of the approach. And we can see here a graph where on the y-axis we have gamma, so the target wealth, and on the x-axis we have the expected shortfall. This graph can be interpreted in two ways. We can interpret this curve as the minimal expected shortfall obtainable for a given value of target wealth gamma. So, for example, by fixing a target wealth gamma, we can see we want to minimize the expected shortfall. And in this case, we see that our proposed policy with kernel methods 4 behaves better than the other one. Or we can interpret this as considering the expected shortfall as a risk measure. And so we say, okay, we want a certain level of risk. I want to choose the policies that maximize the expected gain. So, for example, if I assume an expected shortfall of 3, I see that the policy that maximizes the gain is again the proposed one, that is in dark blue. Then we also compared some histograms that represent the final wealth on test set with a target wealth of 1.08. So these are generated by considering the different scenarios, where the red line, the vertical dashed red line, represents the target wealth, and the black line, the average wealth obtainable across all the test scenarios. And here again, we have the affine policy, the squared transform policy, the naive policies, and the policy with the kernel. And we can see that the proposed policy 4, so that is the one with the kernel, is able to obtain an average wealth that is closer to the target wealth with respect to the other policies. So concluding, the work dealt with financial asset allocation, starting from a multi-period optimization problem. Our contribution is the extension of existing scenario-based control design to nonlinear control using kernel-based methods. And the effectiveness of the approach is tested on experimental real financial data. And the future research is devoted to investigating different kernel functions, as well to extensive experimental validation of the proposed methodology. Here are some references, and thanks for your attention.
Thank you, Mirko, for your interesting presentation. I didn't see questions in the chat. I have a question for you. I would like to know if your comments about the computational complexity and in particular the computational effort of the different policies that you used, and in particular the kernel-based method that I understood is the best one.
Yes, it is in this result, it is the best one, but it's also the most computational demanding, because you have to invert, you may have to invert a big matrix every time you solve this, kernel problem, a matrix that depends on the number of data that, or features that you have. So it can be quite computationally demanding, actually. Yes, this is true.
And in particular, when you have a big number of data, is it possible to reach a result, or do you think that there are some problems?
I think it would be possible to reach a result, because in the kernel learning and more general Gaussian processes literature, there are methods specifically developed to speed up the computation at the price of some approximation. So I think that it can be possible to use these techniques.
Okay, thank you. Thank you very much. If there are other questions, but I don't see any request. So we can move to the second speaker, that is Alessandro Rinaldi. Alessandro Rinaldi will present the contribution titled ICT Services for Electro-Mobility.
Hi, good morning to everybody. Can you see my screen?
Yes.
Okay, perfect. So good morning to everybody. I'm Alessandro Rinaldi, a PhD and engineering here at the Polytechnic University of Bari. I'm also a research assistant, and I work at the Laboratory of Control and Automation at the Polytechnic University of Bari. And my work, my presentation regards the ICT services for electromobility. And the other authors of this work are Fanti, Bartolomeo, Silvestri, Michele, Roccotelli, and Agostino, Marcello, Mangini. So at first, which is the outline and the summary of this presentation, I will talk about the introduction and the research demand. Then I will focus on the smart mobility theme and the concept. Then I will focus in particular on the case studies. This is the LV10 project. That is a European project of the Horizon 2020. And then I will talk more of this project. And in particular, I will focus on the several information and communication technologies, tools, and services that we developed during this project for the electric light vehicles. And at the end, I will talk about some conclusions and the results of this work. So at first, which is the research demand, which is the introduction, which is the framework of this work. At first, I will we have to talk about the transport sector and also the mobility sector. That is one of the main responsible of the production of greenhouse gas emissions that are causing the climate change, the well-known climate change. And in particular, several and many studies, not only in European, but also in the world, show that the most frequent trip is made by the traditional cars. So the citizens usually use private vehicles instead of public transport means, because the traditional car is the main transport mode used. And this caused these have negative effects on the urban traffic congestion and also on the parking shortage, and also is also caused the transport system is not efficient, because we have high levels of air pollution and noise pollution. So to this aim, an evolution and a change of the mobility is required in a sustainable perspective, more with a specific attention to the changing needs of the city and also to the public policies. And this change is also imposed by the United Nations Agenda of 2030 that have the aims to improve the quality of life in the urban area. And so the transition to alternative mobility meets the objectives of decarbonization, decentralization, and also digitalization. A transport revolution, transport change is also can have also important repercussion not only on the environmental aspect but also in the social sphere, because we can also change the mobility habits of the citizens. And nowadays, in the field of mobility, a new transport mode is emerging, more based on the access of the services rather than of the use of the vehicle. We can see, for example, in high use of the sharing system for the use of the vehicle. And in this context, the sustainable mobility can allow the reduction of all the negative effects of this urban area that are characterized by high levels of noise pollution and air pollution. So now we have to define and to have to project, to plan and to change the city towards a smart city. In particular, as regarding the smart city definition, we can have different meanings of these of the smart cities by the different aspects that we can have the smart city. In particular, we can have a smart city on the environmental aspect, on the living aspect, on the governance, or on the economy, and the people aspect. But in this paper, in this work, we want to focus on the mobility aspect, and so how a city can be smart on the mobility aspect. A city can be smart on the mobility aspect if the city develop several technologies in order to improve the urban mobility. So in this, to these aims, the modern ICT solution allows significant improvement in the mobility sector, and especially in the electromobility and also sharing systems. So the ICT tools allow to incentivize and facilitate the usage of electric vehicle by providing several services and ICT tools, for example, booking and brokering services for the vehicle or of the charging point, charging station. We'll also have the services or tool in order to monitor the vehicle and so on. So inside this framework, inside this context, there is the LVTEM project. The LVTEM project, the Polytechnic University of Bari is among the partners of this project. This project is a researcher and innovation action of the Horizon 2020. This project started in November 27, and this project will finish in October of 2020. The aim, one of the aim of this project is to encourage the use of the electric light vehicles inside the European cities. Inside this project, we have 21 partners, and in particular, we have also 6 cities. Inside these 6 cities, we have 1 year. We had 1 year of long demonstration using several electric light vehicles. And in these cities, we also used several ICT tools in order to encourage the citizen to use these vehicles and also to do several operations. Among the other objectives of the project, There is also the aim of develop replicable usage scheme of electric light vehicles based on the deployment of innovative parking and charging services, and also by developing also sharing and rental services. Other aims is also to develop ICT tools in order to facilitate the usage of electric light vehicles and to motivate the usage of this vehicle. Inside the Alta project, we also organized, as talked before, 1 year of long-term demonstration in 6 cities in order to create a big data bank of real driving and usage data and users' experience and opinions on these vehicles, and also on the several ICT tools that we developed. So, starting and focusing on the ICT tools that we developed in this project. At first, in order to define and also to design these ICT tools and services, we at first studied the actual context of the cities by analyzing the existing ICT assets available in each cities. Then we identify also the required ICT assets and also the required ICT functionalities that the several services have to have. And to this aim, we also develop, adapt, and deploy existing ICT tools, application, and services. And also, we also set up the infrastructure for the proper data collection during the demonstration. So, which are the several ICT tools and services that we developed during this project? These are the several ICT tools that we developed. So, we have a booking and brokering app and services in order to book the vehicle and also the charging point. We have a serious game app in order to facilitate and to motivate the usage of the vehicles. We have also an incentive and facilitation platform and app in order to incentivize the usage of the vehicle. We have also a dedicated parking area management of the vehicle, and we have also a fleet and a platform in order to monitor all the fleet of the vehicles by the black box that are installed on vehicles. So I will have also only a briefly description of the several ICT tools and app that we developed. So at first, we developed this booking app. In this slide, we can also see the screenshot of this app that is available on Android. And the end users of this app is the LV10 users. And the main goals of this app is to allow the LV10 users to book vehicle, book charging point, book parking space, and also cancel booking, and also fill in questionnaire, because each app has several questionnaires in order to monitor and to know which is the level of satisfaction of the users versus towards these several ICT tools. And so we can see other screenshot of the app where, for example, it's possible to see we can select the day of the booking, the hours of the booking. We can also select the vehicles, and also we can see if the operation has been successful or not. Then we have the digital coach app. The digital coach app is used by the LV10 users. And the main goals, the main aims of this app is to collect the trips data and collect questionnaire. So to this aim, the users can use this app and also can collect all the trips that he made by the vehicles. And by the score and the trips is important in the LV10 project, because this app is strictly related to the incentive schemes and to the incentive app, because the users with more trips can have more incentives and awards in the project. So we can see some screenshot of this app where it is possible to have the score, the trip score, and so which are, for example, the impact on the CO2 emission reduction, and so on, which is also which are also other data related to the trip distance, duration, and so on. Then we also developed the fleet monitoring tool that is a platform used by the city operator in order to visualize the fleet of the vehicles. So the city operator can have a look at all the vehicles inside the cities, localize the vehicles, and also see the driven routes by the vehicle. So if there is a vehicle that needs some work, is it possible to reach the vehicle and also substitute it? The serious game is developed in order to incentivize and to facilitate the usage of the vehicle. In particular, this app is composed by several questionnaires on the architectural and where there are several questionnaires on the architectural monuments of the city. So by answering to this question, the users can reach and can obtain more score in order to have more incentives and more awards. These are, for example, some screenshot of the app, where, for example, we can see the several monuments in each city, and by selecting the monuments, the users can answer to the several questions that are not only historical but also cultural and cultural topics, and also by architectural and so on. And more answers give to the users more score in order to have more incentives for the users. This is the incentive smart app. So I talked before of this app. So the end users of this app is the Albitan users. The main goal is to incentivize the user of the Albitan services, and also to collect questions. So by this app, the users can have a look on the total points, the total score, which are the available points, and the points that he have used, and also which are the several scores, which are the several awards that he has gained. On the other side of the incentive app, there is the incentive administration console used by the city operators. And by this platform, the city operator can manage the incentive settings and objects by defining which are the rules, the incentive, and the awards that the city gave to the users and also to the citizens. And so each city can customize these rules according to their opinion. And also to the city operator can also manage the general incentive settings. And so, for example, we can see which are the list of rules of type, for example, recharge, and so to the city operator can insert or edit rules of type, for example, kilometer traveled. So by all the answers of the questionnaires that the users answers on the level of satisfaction of the ICT tools, and also on the impact of the ICT tools towards the spread of the electric vehicles, the result that in the smart mobility context, the ICT solution can incentivize and facilitate use of electric vehicles by providing different services that can allow the users to use with a user-friendly interface the several vehicles. The ICT solution ensures high flexibility in order to sustain a good and motivating the experience of electric vehicles users. And the ICT solution can allow the transition, as talked before in the first slides, to the transition to the smart mobility by improving the urban traffic and mobility on the basis of sustainability, innovation, and safe transport. So by this project, it results how the ICT tools are one of the main one of the main aspects that can allow the transition towards towards the electric vehicles. So that's all. Thanks for your attention. I don't know if there is some questions.
Thank you for your presentation. I don't see any request for questions and comments. I would like just to ask you to point out what is the application that appeared very useful for the management purposes of light vehicles.
Yes, of course, one of the main tools that was used by the users was the booking and brokering app, because by this app is it possible to localize the vehicle and also to book the vehicles, and also then to pick up the vehicle and use the vehicle. And so by this app, the user can in briefly minutes can have the vehicles and use it. And other app are also the incentives app, because for the users it's important to gain some incentives and awards that can allow him to use the vehicles. And also by the side of the city operator, the fleet monitoring tool, and so the fleet monitoring platform resulted a significant tools in order to have a look all the fleet of the vehicle, in order to plan the maintenance also of the vehicle, and also to substitute some vehicles that had the problem during the demonstration of the cities.
Okay, thank you.
Thank you.
We can move now to the third speaker. The third speaker is Bartolomeo Silvestri. He will present innovative approaches for electric vehicles, relocation, management, in sharing systems.
Yes, good morning. Can you see my screen?
No, by now.
Okay, one moment. Can you see my screen now?
Yes, okay.
Okay, perfect. Thank you. Good morning, my name is Bartolomeo Silvestri. I'm a PhD of the Polytechnic University of Bari, and I present today a study on innovative approaches for electric vehicle relocation management in a sharing system. And this work is developed with Professor Fanti, Mangini, and Roccotelli. So human activities generate positive and negative impact. These negative impact are also called externalities, and transport sector is not different for this. Transport generates several issues, and the mobility of people, especially in urban area, increase this problem. In the cities, there are high presence of inhabitants, and this trend will increase over the next few years. Transport externalities in urban area are an important theme in the field of research. Several European projects address this issue with different classification, but environmental and economic aspects are the most important. For instance, we analyze 4 different European projects, and the main transport externalities in urban areas evaluated in this project are environmental, energy, economy, travel time, employment, road safety, and quality life and social. It's possible to reduce this externality with innovation. The innovation can concern both technical and organizational aspect. In recent years, considerable progress have been made in the technical areas in different fields, also thanks to the new technologies. Electric vehicles are an example of this innovation, and there are several companies who are investing a lot of money and proposing new models on the market as valid alternative to traditional ICE vehicle. The benefit of this vehicle are to reduce the emission, especially in urban area. The main electric vehicle used on the road in urban area can be classified in this category. We have a pedelec, that are bike with pedal assistance, equipped with an auxiliary electric motor less than 250 watt. After this, we can see e-scooter, seagull, and overboard, that are new urban means of transport for passenger transport and for micro-mobility. These are very useful in the last few months and years. They are fast, agile, light, and easy to carry. So we can use electric car with the different technology developed for passenger transport, electric van, and electric light vehicle, that are a special category of electric vehicle that include small transport means with 2, 3 on the 4 wheels, as moped and motorbike, and as well as quad, tricycle, and quadricycle. Sharing vehicle are an efficient urban mobility system. In the recent year, the several companies are proposing different shared means, bikes, car, scooter, and in many cases they are electric. In the cost of the service, sharing company allow to the client to use pay parking lots and entering in a restricted city area through agreement with local public administration. The advantages of use of this system is to reduce the number of vehicles on the road, with excellent benefit for the city, considering also the average use of private vehicle, that is about 1 hour per day. Sharing system with electric vehicle are the last challenge of several cities in the world that want to reduce the number of vehicles with zero emission means. The main 2 usage schemes proposed by sharing company are station-based and free-floating. In the first case, it's necessary to pick up and leave the electric vehicle in one of the stations spread in the city, based on the availability of the electric vehicle and parking lots. In the second case, it's possible to pick up and leave the electric vehicle everywhere in the city. The sharing system with the electric vehicle is a complex system. There are several issues that is necessary to manage in order to provide a high level of service for users. Alternatively, they will no longer use the service. Firstly, it's necessary that electric vehicles are available in different areas of the city. In addition, electric vehicles require charging activities, especially in a free-floating scheme. Therefore, relocation activities is very important. Moreover, it's important to choose the location of the station and the charging point based on the agreement with local public administration and the permitted available area of use. Finally, it's necessary to consider the time required for charging this electric vehicle. The relocation, based on the mentioned issue, very interesting is to improve the reallocation activities with innovative approach. Relocation activities move electric vehicle from one station area of the city to another in order to ensure the availability in different urban area and to charge vehicle when necessary. A company staff perform this service and it's an expensive operative cost, especially to ensure high level of service and to move electric vehicle to most demand area. The main approach used in the relocation activities are operator-based approach that is performed by company staff and user-based approach, which involving users in the relocation task. With this objective, we introduce the concept of positive incentive related to the concept of nudge defined in the behavior economy. It is said that a set of material or virtual objects that help modify the mobility behavior to obtain reducing of driving and or use of alternative mode. The advantage to introduce the incentive strategy to relocation sharing vehicle with the user involvement are reduce the reallocation cost for the company, engage users to the sharing system with reward to be used for mobility service, and reduce the emission and negative impact, so externality, due to vehicle involved in the reallocation service by company staff. The incentive system proposed involved the users in the reallocation process with 3 levels of incentive. All values are lower than the reallocation cost faced by the company staff. The user accept for the simulation is based on the proposed probability rate. We use this kind of approach. In this slide, we show the flowchart of this method. So there is a notify to the users with an app and is proposed an incentive value. If the users accept, they pick up the vehicle from the station I and go to the station J, defined by the system. If the user don't accept, there are some level of incentive. After this level is notified to the company that vehicle is not reallocated, so the company use his staff to reallocate the vehicle. The proposed approach is based on an optimization problem with a goal to minimize the total relocation cost. Some assumptions are necessary to set the problem. It's considered an electric vehicle sharing system with station-based scheme. The distance and cost of the relocation service are defined. A minimum and a maximum number of electric vehicles are defined in each station. Number of electric vehicles in charging during relocation are defined and excluded by the optimization if the electric vehicle can't carry can perform the trip. And the number of electric vehicles in each station before the relocation is known. The problem is an integer linear programming problem with the binary decision variable. It is formulated as follows in the centralized optimization approach, both for operator-based and user-based approach. In this slide, we can see the ILP1 is the operator-based approach, so with the company staff. Now I show you the distributed sorry, one moment. Okay, this is the centralized optimization approach with the user-based for ILP2, and in this formulation is considered also users and incentive value for the users. In this case, we propose the distributed optimization approach with the local integer linear programming problem, both for operator-based and user-based approach. In this slide, the formulation is presented for L-ILP1, and in this second slide, there is shown the L-ILP2 with involving users. After this, we compare the two approaches, so with operator-based and user-based. We introduce the distributed optimization approach because it is very useful in the case of a large number of electric vehicles and the number of stations, because the computational complexity is exponential. Therefore, in this case, it's possible to solve centralized problem with a large number of variables in a very high time, or in some time it's not possible to solve it by software. Therefore, the use of the distributed approach is very useful to solve the problem, and the analysis of the computation show the difference between the two approaches as the number of variables increases. A case study simulation is proposed with 500 number of vehicles, 30 stations, 400 users available in the relocation, a minimum and maximum number of vehicles in each station equal to 10 and 30, a relocation company cost of €1 per kilometer, and a distance source matrix between stations defined with a level of battery for each vehicle known. So I present this table with this number, and after the simulation, we obtain this result. The first is the solution with the operator-based approach, so involving in the relocation the company staff. In this case, we have a total relocation cost, equal to €45 per day. In the second case, in the user-based approach, always in the centralized optimization approach, we have a new relocation process. In the red line, we can see the users involving in the process, and we have a reduction of the total relocation cost of about 12%. In the second case, we use this approach in the distributed optimization optimization strategy. So also in this case, we can see a reduction of the total relocation cost, but the value are higher than the first case with the centralized approach. It is normal because it is not an exact approach, but it is a local integer linear programming problem, and therefore we have a reduction of time, or computational time, but a result that is higher than of the first case. In conclusion, we can say that a method to solve the electric vehicle relocation problem in a station-based sharing system is presented. The centralized approach is proposed in two aspects of the problem. The first integer linear programming problem is formulated to centrally manage the relocation process with the operator-based approach with company staff. In the second case, an integer linear programming problem is modeled to solve the electric vehicle relocation problem with users-based approach, so involving users and applying a multi-level incentive scheme. In case of large system, so with a high number of electric vehicle and the station, a distributed optimization approach is applied to reduce the computational complexity of the centralized approach. the station communicate each other and iteratively to solve local integer linear programming problem and to reach a consensus-based solution. The centralized distribution approach are applied to some instance of the electric vehicle relocation problem and to a large case study. The results show the advantage of using the incentive and the distributed procedure involving users. In the future work, we involve the proposed method in the electric vehicle relocation with a free-floating sharing system. This study is based on the LV10 project, an Horizon 2020 project that want to encourage the use of light vehicle also with a sharing system usage scheme. Thank you for your attention. If you have any question, I'm here.
Thank you, Bartolomeo. And I think that we haven't any questions from the panelists and the attendees. And I would like just that you clarify how the distribute optimization is performed.
Yes.
Who performs this distribute optimization?
We use an algorithm to use this approach, and this algorithm is based on a local optimization that is compare the distance between the different stations and the cost of these. It's possible because we have all data of this, so we reduce the integer linear programming problem with few number of stations, and iteratively we insert in this problem a new station and leave another, because the computational complexity of the problem increased with a high number of vehicles, but with a low with few station or vehicle is possible to have very high result. So for this reason, it's possible to use this approach and solve the problem with the distributed approach.
Okay, thank you. So we can move to the last speaker, that is Gioacchino Manfredi. He will present optimal allocation of network resources for QoE-Fair video distribution.
Good morning. Can you see my screen?
Yes.
Okay. Thank you, Professor. And good morning, everyone. My name is Gioacchino Manfredi, and I'm a PhD student at the Polytechnic of Bari. And today I will introduce our work conducted with Luca De Cicco, Saverio Masco, and Vittorio Palmisano concerning optimal allocation of network resources for QoE-Fair video distribution. Well, to begin with, it is well known that an increasing fraction of users prefer to consume videos over the internet rather than using classical TV broadcast channels. And for this reason, the goal of online services is to provide and guarantee the best possible quality of experience to users, and also to limit service abandonment. Well, today the standard approach to solve this problem is to decouple the problem into two parts. In the first place, a video delivery network is implemented through the content delivery network. That is used to scale the network resources as the traffic load increases, and also to equally provide users with the same share of network bandwidth, thus adopting a quality of service fair network resources allocation. Well, then the players at the client side run adaptive bitrate algorithms that are used to adapt the video content to the bandwidth allocation and to the user device to obtain the best possible and individual QoE. Now, to better understand the issue we are tackling, let us consider the following example, where we have two users sharing the same bottleneck, connecting them to a video provider. And these two users, of course, request a video to this video provider. And suppose that user one has a high resolution, so for example, 4K resolution, and user two has a 720p resolution. Well, in this case, the current delivery networks employed today equally allocate network resources to users. And so in this case, exactly half the bottleneck would be assigned to user one and half to user two. So we will have two flows going from the video provider to the users. And of course, we will almost surely, we will have that the two users will have very different visual qualities. In fact, if we want to guarantee visual quality fairness, we need to allocate more bandwidth to user one, that is the high resolution user, and less bandwidth to user two, that has a low resolution device. But if we assign the same bandwidth share to both users as we have done, in this case, as we can see, the two users will experience a dramatically different visual quality level. And this, of course, will penalize high-resolution devices in reality. And of course, this results in QoE unfairness. So to guarantee video quality fair distribution, we need to differentiate the bandwidth shares allocated to users based on their device resolution. So in our solution, what we propose is to implement a centralized control employing software-defined networking. In fact, SDN switches are able to differentiate the bandwidth shares allocated to users, in this case, based on their device resolution. And so if we look at our previous example, the SDN switch will be able to assign more bandwidth in the bottleneck to user one and less to user two. And in this case, it will be more likely that the two users will experience the same visual quality, or at least a similar visual quality, thus achieving quality of experience fairness. So this is the case, the previous case that is adopted by current delivery networks. But if we implement a centralized control with a software-defined networking, we will assign more bandwidth to user one that has a high-resolution device and less bandwidth to user two. In this case, of course, the two users will have a similar visual quality, or ideally the same visual quality, thus guaranteeing the QoE fairness, which is what we want to achieve. So now let us go more into the detail and see how a video is encoded in the Dutch standard. Well, a video is firstly divided into chunks of fixed duration, and then these chunks are encoded at different levels, so that the Dutch standard can encode a video at level 1, so for example at 360p resolution, and then switch to level 2, and so on. So the adaptive bitrate algorithms running at the client side in this way will be able to choose the level of the video chunk available according to the available bandwidth and to the device resolution. So what we have adopted in our solution is a multipath approach. In fact, in this way, the SDN switches will be able to assign a video session to multiple slices, that is, to more than one path. And now the goal is to compute the size of these slices for each path, that is, the amount of bandwidth allocated to each slice, in such a way that QoE fairness is achieved among the users. And so to better understand this, let us look at the figure. We have centralized control receiving video requests from the client, and these video requests are simply represented by tuples containing the source node, the destination node, the requested video, and the user device resolution. Well, then the centralized control implements an optimization framework that aims at assigning these video requests to multiple slices and to optimize them so that QoE fairness is achieved. then this solution is actually implemented on the network, as we can see from this example. So for instance, server 2 will be delivering a video to user 2 using 2 parts as highlighted by the green lines here. And these parts, of course, will be assigned by the centralized control, as we have said, and they will be optimally sized in such a way that they can cope with the shared bottlenecks, as in this case. So for the optimization phase in the central control, we have considered the multi-commodity flow problem, whose objective function, as we can see, enforces a weighted proportional fair network resource allocation. And to better understand this, we need to define the concept of demand. A demand is the aggregate of all the video sessions, of all the video requests coming from the same source node, requesting the same video from the same video provider, and coming from users having the same device resolution. So in other words, the demand is the aggregate of all these tuples that are equal. And now capital XT is the total bandwidth allocated to a demand D. With XTP, we indicate the slice bandwidth of demand D for a specific path P, and of course, in the constraints, the sum over the parts of all these slice bandwidths will be has to be equal to the total bandwidth allocated. Now, if we look at the objective function, we can see that these WD are the weights associated to demand D, and of course, what we want is that. Of course, the larger the weights associated to, we want large weights for high resolution devices for the reasons we have said before. So to do this, so to compute the weights in this way, we use the VMAF metric. And in particular, what we do is to fix a specific video and a specific user resolution. We can see this in the picture. So we have 2 4K resolution user and 1080p resolution user. Then we, for each of these resolutions and for each video, we use the VMAF metric to extract a set of points mapping the bandwidth to the visual quality. And then we use a parametric logarithmic fitting function in this form, a log x, where a is the parameter that fits these points, as we can see from the continuous line. And of course, these curves, for each of these curves, we will have a specific value of the parameter a. And this means that we can now define the weight as 1 over a to the beta, where beta is a positive parameter that has to be properly tuned, as we will see. And notice that in this way, we have attained what we wanted. That is, we wanted to assign large weights to high resolution devices so that they get more bandwidth. And in this case, if we look at the 4K resolution user, the weight is higher with respect to the 1080p resolution, which is lower. So this is a good way to achieve this objective. Now, at this point, we have all what we need to solve our optimization problem, but this problem is intractable due to the high number of couples video user resolutions. And this is due to the fact that usually we have a huge size of the video catalog. So to overcome this problem, we propose to partition the video catalog into a tunable number K of clusters. And in this way, once we do this, we can redefine the concept of demand, containing all the users having the same resolutions, requesting videos belonging to the same video cluster. And this means that, of course, in this case, we will have less variables in the optimization problem. And so the multi-commodity flow problem can be made tractable. Now, how do we perform such a clusterization of the video catalog? Well, once we fix the user resolution, we consider the visual quality profiles of all the videos in the video catalog. And then, of course, these visual quality profiles are obtained through the VMAF metric we have talked about before. And then we partition these profiles according to their similarity. Well, more precisely, what we do is to consider the weights associated to each of these profiles for each video and the minimum bandwidth B over bar associated to each video to obtain a visual quality equal to 1, that is the maximum visual quality. So in the end, we end up with a set of points. Each point will represent a video. And on these points, we can run a clustering algorithm. In our case, we have run a k-medoid clustering algorithm. And so we obtain a set of clusters, as we can see from the figure. And in each cluster, we will have a medoid point to which, of course, a weight will be assigned, as we can see. And this weight will represent all the videos in the cluster in the optimization problem. So, of course, if the number k of clusters is low, we will have few clusters very big. And so all the points in the clusters will be, the approximation of all these points with a medoid point will be worse. And this results in worse performance in terms of fairness, as we will see. So we need to find a trade-off to choose this number k of clusters. So we have implemented our proposed weighted proportional fair resource allocation in the Python simulator using CVXPy, and we have compared it with a baseline case that does not differentiate users according to their user resolution. And so what we have considered is a video catalog of about 204K videos fetched from YouTube, and that run our simulations on a real network that is the GAR network, and we have considered 3 possible user resolutions: 720p, 1080p, and 4K, and 2 possible number of clusters, that is 3 and 5. So now the first simulations show the trade-off between the average visual quality obtained by the users in the network and the fairness for the case of 1, 2, and 5 possible paths, since we have considered the multipath case. The points represented in the figure represent the total traffic load in the network. And if we look on the left, these lines represent the baseline case. And we can see that as the total traffic load increases, and so it goes from 100 to 500 gigabits per second, the average visual quality tends to decrease, and also the fairness. While when we pass from 1 path to 5 paths, the average visual quality levels stay almost the same, while the fairness tends to increase. Well, now, if we look on the right at the proposed approach for the case of 3 clusters in blue and 5 clusters in green, we can see that while the average visual quality values are quite comparable with the baseline case, we can see that the fairness has substantially increased. That was our goal. And this is due to the fact that the standard deviation of the visual quality associated to the users in the network in the proposed approach is far lower with respect to the baseline case. And this comes from the definition of fairness. So as expected, the case of 5 clusters seems to be the best trade-off with respect to the case of 3. And I want to remind that we cannot increase this number k of clusters as we want, because increasing this number k means making the optimization problem harder to solve and eventually intractable. Now, let us partition the video sessions by user resolution. So, and since we have considered only 3 possible user resolutions, we will end up with only 3 curves representing these CDFs. And now on the left, we have the baseline case where these 3 curves are quite spread out, and they underline the QoE unfairness that is present in this case. And in particular, what we can see is that high resolution devices, so 4K resolution devices represented by the green line, will be penalized, highly penalized with respect to the other devices. Well, if we turn to the proposed approach, in this case, we can reach better levels of fairness, far better levels of fairness. And this depends on the tunable parameter beta used to define the weight. So for example, if we set beta equal to 1.1, what we have is that these curves, as we can see, are much closer, and this underlines the fairness, that we have a higher level of fairness with respect to the baseline case. But if we set beta equal to 1.4, we can see that we almost reach fairness optimality. And these curves mean that almost all the users in the network will experience the same visual quality independently of their user device resolution, which is what we wanted. So to conclude, we have considered the problem of QoE-Fair video distribution to heterogeneous users. And to this end, we have implemented a multipath, multi-commodity flow optimization framework used to assign the slices and to optimally size them. And the simulations have shown that the proposed approach outperforms the baseline case, which is notice the approach currently used by video delivery services today. And well, an important future work could be considering other real networks and running our simulations on these other networks to possibly make comparisons. So thank you for your attention, and if you have questions.
Thank you, Gioacchino, for your nice presentation. I have a question for you. It is not clear to me if the solution that you are finding must be obtained in real time, in other words, online. Because in such a case, the computational effort is a huge problem. It's a very, very terrible problem.
Well, there are some parts that are computed. Actually, of course, this optimization problem is not online, it's not real time, but is offline. In fact, it's not useful actually, because as we can see, for example, the clusterization of the video catalog can be made offline, and the video requests that come from the users of course need some time, so we have all the time to solve the optimization problem. And it is not really computationally, as long as we choose the right number K of clusters in the video catalog, it does not require a long time, so it's not really computationally demanding. And also there are many other things that we can compute on offline. So for example, the weights and all the rest. So these are all the parameters that actually represent and characterize the optimization problem. And so there is no need for the online optimization.
So it's possible
to do it offline.
To apply.
Yes.
Oh, okay.
Yes,
Okay.
yes, surely.
Are there any questions from panelists and attendees? Okay. If there aren't any questions and comments, I can close this section. Thank you for attending this session, and I hope that you enjoy the complete workshop and conference in this afternoon and tomorrow. Good morning, good afternoon.